So here it is, our last problem in chapter 3 that we're going to work on, and it pretty much puts everything together. It has balancing chemical equations, it has stoichiometry, it has limiting reactant, it has solution chemistry. So what I hope to do after I show you when we set up this problem is you've really already done a problem just like this. But let's go ahead and set up our roadmap, and then we'll compare it to a problem we've already done, and you'll see that it's very similar. So this problem says in a simulation mercury removal from industrial wastewater, 0.05 liters or 50 milliliters of a 0.01 molar mercury 2 nitrate solution reacts with 0.02 liters of a 0.1 molar sodium sulfide solution. How many grams of mercury 2 sulfide form? We also need to write a reaction table for this process. Well, I'm going to give you a little bit of a heads up. We already did a problem just like this when we did sample problem 320. What was different is we were looking at masses of samples. Now we're going to be looking at volumes of samples because we're talking about solution chemistry. But as we set up our roadmap for this, I'll flip back to the roadmap that we designed for problem 3.20, and you'll see that it's exactly the same. So we're going to treat this problem the same as we did then. We're going to have formulas that we have to write from names that's in the problem. And again, that's practicing our chapter 2 skills. From these formulas and from the words in our problem here, we have to write a balanced chemical equation. From this balanced chemical equation, and as we'll see when we write the reaction equation, we'll see that since they give us two reagents, we're going to have to figure out who is the limiting reactant. Once we figure that out, then we'll be able to determine how much product is formed. And as the problem indicates, we're going to want to draw a reaction table for this process to allow us to keep track of all the different quantities of materials that are there. Okay, so let's set up our problem here. We've got mercury 2 nitrate. So mercury 2 means it's a mercury 2 plus ion, and then nitrate is -1. So we're going to need to have two nitrates. So this is going to be HgNO3 2 aqueous. Okay, so mercury 2 nitrate reacts with sodium sulfide. So again, sodium is Na plus, sulfide is S2 minus. So we're going to have Na2S, and again, that's an aqueous solution. Chemistry happens that we're going to generate mercury 2 sulfide, so HgS. And again, we're going to also have, this is one of those double displacement reactions, 2 NaNO3. And that's aqueous. I knew that this was going to be 2 because I had 2 sodiums here and 2 nitrates there. So again, that was just kind of a quick, easy way of balancing that. Mercury's balanced, sulfur's balanced. We're ready to go here. So we translated our names into chemical formulas for all of these species. We wrote a balanced chemical equation that showed the reaction between these two. Now we have to add underneath our balanced chemical reaction here some information that's also provided in our problem here. So they tell us that we have 0.05 liters of a 0.01 molar mercury nitrate solution. So I'm going to write that under here, 0.050 liters, and our concentration is 0.010 molar. And then sodium sulfide, we have 0.02 liters and 0.1 molar. And so the question asks us, so again, this is information we know, and where we want to go is we want to find out how many grams of mercury 2 sulfide forms. So mercury 2 sulfide is going to be a solid here. So in terms of our question here, we want to know how many grams we're going to form here. Now again, in this problem, if all we were given was that we had this amount of sodium sulfide, we could walk using molarity from these parameters to moles, walk over to moles using the chemical equation, and then using molar mass, we could walk to grams. But we could also do the same walk here. We could go to moles using molarity of this, use our balanced chemical equation to get to moles here, and again, using molecular weight could get us to grams. So the question is which walk do we use? And that's the idea of one of these is going to be a limiting reagent. So we have to figure out who's going to be the limiting reagent. And how you do this is pretty much, well, we have to go on both of these walks. And so what we're going to do here is we see on the roadmap that they basically show us in your textbook is they show those same two paths. You actually have to take and walk each of these paths to find amounts. You can stop at moles, of mercury sulfide. But whoever makes the least amount of mercury sulfide is going to be your limiting reactant, and you choose that one to go on and do this last step where you use the molar mass of mercury sulfide to convert those moles to grams. So we are going to set up this problem exactly the same way that we did this other problem. So I'm flipping back to problem 320 now, so you could see we had the same thing. Balanced chemical equation. We had masses of two reagents. We talked about the walks that we could take for each of them to create a certain number of grams of nitrogen. We went through and took each of these calculations to the number of moles of nitrogen that we could produce, and we figured out who made the least amount of nitrogen, and that was our limiting reagent. So this problem that we're doing now is not any different, except the walk that we have from the material that we're given in volume to moles is now going to be molarity. The walk that we did in problem 320 from what we were given to moles, since we were given mass, we used molar mass to walk there. So again, these problems really aren't that different, but we're going to have to treat this one just the same, and we're going to have to do this walk for both of these species. So let's do it first for the mercury 2 nitrate. So for this mercury 2 nitrate, we're going to have 0.050 liters of mercury 2 nitrate. Again, I can walk between the molarity, so 1 liter of this mercury 2 nitrate solution is going to be equal to 0.010 moles of mercury nitrate. Now, only because this problem asks us to write a reaction table, I'm going to stop the calculation at this point just to get a value, because this will be used as part of our reaction table. This is 5.0 times 10 to the minus 4th moles of mercury 2 nitrate. And remember, the reason we stopped is this is the number for our ICF table, for our reaction table. Now again, I walked to moles. I can use my balanced chemical equation to walk to moles of mercury 2 sulfide. So in this case, it's a 1-to-1 relationship. So I have 1 mole of mercury 2 nitrate makes 1 mole of mercury sulfide, and the answer to that is 5 times 10 to the minus 4th moles of mercury 2 sulfide. Okay. So we're going to do the exact same walk, but now with our other reagent that we're given an amount of in volume, and we know the concentration. So here's our sodium sulfide, 0.020 liters of sodium 2 sulfide, 1 liter of, I shouldn't say sodium 2, it's sodium sulfide, is 0.10 moles of sodium sulfide. And as I said before, I'm going to solve this calculation at this point because I'm going to get a value that will become part of my reaction table. So 2 times 10 to the minus 3rd moles of sodium sulfite. Now, in this case, we can look at here and we can see that it's also a 1-to-1 relationship. So 1 mole of sodium sulfide makes 1 mole of mercury 2 sulfide, and so that's 2.0 times 10 to the minus 3rd moles of mercury sulfide. So just again to remind everybody where we get these pieces of information, this unit conversion came from our molarity, this unit conversion came from our balanced chemical equation, and for both of these, in this case, math does not matter. In this case. So mathematically, these ones aren't going to change the value in this quantity. But I still want everybody to get into the habit of doing that, because if for some reason we wanted to talk about sodium nitrate, it would matter. But what we do here is we look at these two values, right? We see that 5 times 10 to the minus 4th is smaller than 2 times 10 to the minus 3rd. Remember, don't just get and look at the 5 here and say, oh, that's bigger. It's 5 times 10 to the minus 4th. So this is actually a smaller number. So that means this guy is our limiting reagent. Mercury 2 nitrate is our limiting reagent. And just to remind everybody, right? Things that we talked about in sample problem 3.20. You can't use amounts of reagents to determine the limiting reactant. So we couldn't compare the masses that we had. We couldn't compare the moles that we had. We had to compare the moles of product that we made. Same thing with here. We can't compare the volumes that we start with of these materials, right? If we would have said that we had only 20 milliliters of this guy. That's not the limiting reagent. And in this case, the number of moles of reactant that we have will also equal the moles of product that we make because the stoichiometry is 1 to 1 to 1 between these three species. So in that case, you could compare that, and I'm okay as we move forward in these problems if you're able to see that. But if you get it wrong, if you make a wrong assumption and there's nothing to show your work, there's nothing, unfortunately, I can do for you in terms of partial credit. Okay, so what we're going to do now is we're going to treat this problem just like we treat this one in 320. We're going to set up our reaction table, and then we're going to use that to calculate our final answer. Okay, so coming again to a new piece of paper here to continue this problem. Reaction tables are made by starting with a balanced chemical equation on top. So we've got our mercury 2 nitrate plus sodium sulfide makes mercury 2 sulfide plus NaNO3. So equations form the first row of our reaction table. Quantities are always in moles. And the three rows that we have that follow that are initial, change, and final. So for our initial columns, we're going to use these values that we just determined here. That we have 5 times 10 to the minus 4th moles of our mercury nitrate, mercury 2 nitrate. Again, I don't need to write units with these because we know that only moles go in our table. So all of these are going to have units of moles. For sodium sulfide, we have 2 times 10 to the minus 3rd moles. And again, those values are what's given initially in the problem. Since this is the initial part of the reaction, they haven't been reacted yet. We have no product. Okay? The change column, as we mentioned in our previous problem, is the most difficult one to kind of determine. It's usually where mistakes are made. Again, if you need to look back at the sheets here and look back at problem 3.20 for some help, but again, there were some sheets that we handed out as to how we create these ICF tables. Okay, so for this change column, remember the change column is propagated from our limiting reactant. And since we just calculated that mercury 2 nitrate is our limiting reactant, this is the cell essentially that we start with in propagating this table. In limiting reactant problems, this value will always be the same as your initial column. Because it's the limiting reactant, it's completely used up. We indicate that things that are being used up have a minus sign, so our reagents will always have minus signs. Our products will have plus signs. So, and also our final column we really get by adding the initial plus the change cells. So add these two together and you get 0. Again, that should be a hallmark of your limiting reactant. Your limiting reactant should have 0 at the end. Now again, how we propagate the rest of these is we have to use a balanced chemical equation to translate the differences. I'm going to come over here and kind of show this guy first because this is the only one that's truly going to be different. For example, if we have 5 times 10 to the minus 4th moles of our mercury 2 nitrate, and we want to change who we're talking about, we could say that 1 mole of mercury 2 nitrate equates to 2 moles of NaNO3. That's who we changed that who we're talking about here. Moles of mercury nitrate go away. We're left with moles of NaNO3, and we can see that it's going to be twice this value. So that's how we get a value of 1 times 10 to the minus 3rd for here. Okay? And hopefully everybody sees that because the stoichiometry is 1 to 1 to 1, all of these are going to be the same values, except it's going to be that much lost for our sodium sulfide and that much gained for our mercury sulfide, right? Reagents are going away, so they have minus signs. Products are appearing, so they have plus signs. Again, our final column we propagate as the initial plus the change values. So when we add these two together, we see that we have 1.5 times 10 to the minus 3rd moles left over of this reagent, or in excess. Okay, if you ever get a negative number here, that indicates you probably made a mistake with this problem. Same thing here as we have 5 times 10 to the minus 4th, 1 times 10 to the minus 3rd. So that's our reaction table, and now we're ready to go on and finish this problem. We know, based on our limiting reactant calculation and our reaction table that allows us to keep track of everything, that we are going to make 5 times 10 to the minus 4th moles of mercury 2 sulfide. The problem asked us to calculate how many grams of mercury sulfide are going to form. That was what we wanted to find out, how many grams of mercury sulfide we're going to form. So we have the moles of mercury sulfide that we're going to form. So again, our last walk here is to use the molar mass of mercury sulfide to figure out the number of grams that we make. So 1 mole of mercury sulfide is 232.7 grams. That works out to 0.12 grams of mercury 2 sulfide. Again, looking at the number of significant digits that we have 2 significant digits for all of the quantities that are provided, so 2 significant digits in our answer. And that is the last problem in Chapter 3. So again, to recap, skills that were important from Chapter 3, right? We had the concept of the mole, writing empirical and molecular formulas, balancing equations, stoichiometry, reagent quantities, product quantities, limiting reactants, calculating yield, and then the problem again we just worked on was doing all of that within solution.